going to take a look at a conservation of momentum problem that involves a collision. And this collision will be an elastic collision where two objects come together and hit, and then they move apart again. Now, what we're going to do is we're going to create a conservation of momentum bar graph diagram. That's going to help us kind of organize our information. You're not going to always have to create one of these. We're going to kind of learn to do these problems with the bar graphs, but it's absolutely possible to do the problem without it. And on tests and things, it's going to be your choice whether you want to create a bar graph or not. Then we're going to write a conservation of momentum equation, which is very important and is always going to be required. And then we're going to learn how to solve for a variable. Now, this is a pretty simple collision. And, as problems get more complicated, you do the problem the exact same way. You're just going to have, slightly more complicated situations. Okay, I'm going to zoom in here a little bit on the problem itself. We have a candy-filled piñata hung from a tree for Esmeralda's birthday. We have, during an unsuccessful attempt to break the 4.4 kilogram piñata, Esmeralda cracks it with a 0.54 kilogram stick, moving at 4.8 meters per second. The stick stops, and the piñata undergoes a gentle swinging motion. Determine the swing speed of the piñata immediately after being cracked by the stick. All right. Now, let's take a look here. The first thing we always like to do here is we want to circle and mark up the text of the problem so that we know what we're dealing with. I'm going to just zoom in a little bit to the problem to make that a little easier. So what do I actually know here? First thing I know right here is the mass of the piñata. And I'm just going to mark that with the mass of the piñata. Then I know the mass of the stick. I'm going to mark that as the mass of the stick. I know that the stick is initially moving at 4.8 meters per second. So that's going to be the initial velocity of the stick. It doesn't tell me anything about the piñata, but I'm going to assume the piñata is just hanging there and it's still, it's not moving before the stick hits it. Now, when the stick hits it, it says the stick stops. And so my after velocity is going to be, I'm going to make it that little V prime of the stick. And the piñata undergoes a gentle swinging motion. And then it tells us determine the swing speed of the piñata. So what we're actually going to look for and solve for is how fast the piñata moves after we hit it with the stick. Esmeralda hits it with the stick. Okay, so I have my basics here. Next thing I'm going to do, I'm going to take a look at this bar graph. Now, the bar graph here, it's basically showing us a before and an after, an initial and a final representation of the situation. And in between them, right here, this is where we have our collision. Okay? So that collision between the stick and the piñata is occurring right there. Initial means before the collision, and final means after the collision. So what I'm going to do here, I'm going to write in the piñata. I'm going to write in the stick. And if I'm looking here, the piñata is going to have a mass, it's going to have a velocity, and it's going to have a momentum, okay? And I'm going to try to write those in. I'm going to have to zoom in a little bit here to make that work, okay? So I know that my piñata is 4.4 kilograms. And I've already said that my assumption is that the piñata is just hanging there. So it's going to have a velocity of 0. And remember, mass times velocity equals momentum. And that's going to mean my momentum is 0. Now, if I look here, here's 0. Here's the positive momentum and the negative momentum side of the bar chart. Now, at 0, I'm just going to kind of put a line, kind of a slightly heavy line on the 0 for my piñata. And we'll take a look at the stick before the collision. So the stick is 0.54 kilograms. Then it is traveling at 4.8 meters per second. And I'm going to have to do that little bit of math, okay? So I'm going to get my calculator out. And I'm going to take 0.54 times 4.8, and I'm going to get 2.6, and my unit there is a kilogram meter per second. Okay, so I don't really have room to write it there, but that's okay. Now, my total momentum, okay, my total momentum before the collision here would then just be 0 plus 2.6, so it'll be 2.6 kilogram meters per second. And I'm just going to write that there to keep track of it, okay? And I can make a little bar graph. I'm going to assume the stick is swinging in the positive direction. I'm going to say this is 1 kilogram meter per second, 2, 3. 2.6 would be about just a tiny touch over halfway. And I can create a bar graph and just color that thing in. And that takes care of the situation before the collision, okay? I'm going to now kind of slide over here, and I'm going to do the same exact thing for after the collision, okay? Now, I'm not going to rewrite piñata and stick because I don't have a lot of room here, but I'm going to keep everything in the same color. I'm going to have a mass, a velocity, and I'm going to have a momentum after the collision for the piñata and for the stick. So, for the piñata, my mass for the piñata is still 4.4 kilograms. So I'm going to write that in, 4.4 kilograms. My new velocity for the piñata, if I look on here, that's actually what I'm solving for. So I don't have a number for that. So I'm going to have to just write my variable in. It's going to be the new velocity, which means I give it that little prime mark, and it's for the piñata, okay? So that's my variable, and I can't calculate a momentum because I don't know the velocity. Now, for my stick is still 0.54 kilograms. And it says that the stick stops after it hits the piñata. So what that means is that my velocity after is going to be 0. And that gives me a momentum afterwards for the stick of 0. And I can draw that 0 onto the 0 line of my bar graph. Okay, now, here's a couple of tricks. Number 1, conservation of momentum tells us that the total amount of momentum before the collision has to equal the total amount of momentum after the collision. So if my total amount of momentum was 2.6 kilogram meters per second before the collision, it has to be the same after. So I can write this in here that the total momentum has to equal 2.6 kilogram meters per second. Think about what that means. If the total has to equal 2.6 and the stick has 0, then all 2.6 has to be in the momentum of the piñata, which makes the piñata's total momentum equal to 2.6 kilogram meters per second. Now, what you actually have here is a little equation. And you can solve that right now. In some situations, like these simple problems, you can solve that right now and be done, okay? You can solve for V prime for the piñata and you're done. What I'm going to do now, however, is show you the full process, because for more complicated situations, you're going to need to know how to do the whole problem. That's going to involve actually writing a conservation of momentum equation. Now, what that means is that I'm just going to write out all the formulas for the total momentum before the collision and the total momentum after the collision, and I'm going to set them equal to each other. So I'm going to put my equal mark like right there where the collision is. Now, for before the collision, my piñata would be the mass of the piñata times the velocity of the piñata plus the momentum of the stick, which would be the mass of the stick times the velocity of the stick. And that has to equal the mass of the piñata times the new velocity of the piñata. It gets that little prime mark. Plus the mass of the stick times the new velocity of the stick. So all I've done is I've taken what I've put into that bar graph and I've used it to write a conservation of momentum equation. I'm going to use that conservation of momentum equation now to solve for that term, the velocity of the piñata after the collision. And here is how I would do that. I'm just going to slide this up here so I can see. I'm just going to rewrite the conservation of momentum equation just to show you all the steps. So I have the mass of the piñata, velocity of the piñata beforehand, plus the mass of the stick, velocity of the stick beforehand. That is going to equal the mass of the piñata times the velocity of the piñata after the collision, plus the mass of the stick times the velocity of the stick after the collision. Now, we've already calculated all these out, and we've already said a couple of things. Number one, the initial velocity of the piñata is 0, so this term goes to 0. And I know that after the collision, the velocity of the stick is 0. So this term goes to 0. And what I'm left with when I fill in my numbers is the mass of the stick, which is the 0.54 kilograms, times the velocity of the stick, which is the 4.8 meters per second, equals 4.4 kilograms times the new velocity of the piñata, which means that 2.6 kilogram meters per second equals 4.4 kilograms times the new, and put a hat on that one, new velocity of the piñata. Now, I am solving for that term right there. The way I would get that all alone is I would divide both sides by 4.4 kilograms. I'm going to slide this. I'm going to need to make it a little smaller. And this divides to 1. Kilogram divides to 1. And I'm left with taking 2.6 and dividing it by 4.4. And that comes out to 0.59 meters per second equals the final velocity of the piñata. And that is your answer. Now, notice that this step right here is equal to this equation right there. So sometimes that bar graph enables you to take a quick shortcut, okay? Not always, because sometimes it's going to be more complicated. But if you can do it from there, you're welcome to do it from there, okay? Whatever works best for you. And make sure you always box your answers. You would show all of your work. And let me just get this so that you can see the whole problem in one place. And that's how you would do a simple elastic collision problem with a momentum bar graph, a momentum conservation equation, and solving for an unknown variable using your conservation of momentum equation.